Hello, everyone. Welcome to a late edition of the Binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Also, an important note, this is our last podcast of 2023, and we'll be returning on January 8th and 9th, and we will be switching formats as well to do the recordings of the podcast instead of streaming them live. Not to say we'll completely cut out live streaming, but just the podcast will probably be VODs going forward.
Yeah, at least we'll give that a try for now. In the meantime, I've talked several times in the past about wanting to do kind of prep streams where I'm choosing the topics and going through getting notes on them. So still having a chance to talk about all of these, just maybe not as the podcast itself. So you'd be able to check out those streams, which probably won't be scheduled, but just likely to happen in the days leading up to an episode. Which will hopefully still give us some Twitch streaming and interaction, but more focused on the fact that it's a stream and that interaction rather than doing our podcast as a stream.
Yeah.
And we'll try that out. Maybe it'll work, maybe it won't, but gives us some nice options gives us the ability to kind of polish the episodes a little bit more.
Exactly, yeah. Once again, apologies for this episode being so late, not only in terms of like 2 days late, but also late at night. I caught the brunt of a cold right on Tuesday when we normally do these. I'm still not completely over it, so I'm probably not going to talk too much. But we wanted to get this one out, especially where the bounty episode went out this week, and the OCD was kind of triggering, where it's like, I really don't want to leave it on an odd episode number. So, I was determined to push through and try to get one out this week. So we do have some topics together. So I guess we can jump into that right now. So our first topic is a white paper on RetSpill, which deals with leveraging spilling of user data on the kernel stack in order to perform kernel exploitation. So this is a bit of a long paper, but the concept is fairly simple. And the idea is how to get a good exploit strategy going for when you have a control flow hijacking primitive, or a CFHP as they abbreviate it. And what they're talking about there is if you get into a situation where, say, you have a vulnerability that you manage to exploit in order to get control of the instruction pointer, either through hijacking a function pointer in an object, or very rarely a return address or something like that. Just the ability to have control over the instruction pointer. Where do you go from there?
Let me clarify, sorry. This is specific to within the Linux kernel. This isn't a generic technique for anything. It's specific to trying to take advantage, or a technique to take advantage of these issues with, I think they have one of the slides here. Yeah, kind of shows the required primitives for different techniques. So like ret to user, you just kind of need the hijack and you return to user space. Can't do that anymore because of the SMAP protection, but like that's all you need. And they have a few other things in here. Whereas this RetSpill for the scenarios work in, just requires that hijack primitive and the code leak, or the kernel leak, kernel address code base leak, I think.
Yeah, so that is a good shout with it being exclusive to Linux kernel. The way I was like phrasing it there, maybe that was a little bit ambiguous. So
yeah, I don't think you actually mentioned Linux kernel yet, so I want to jump in and clarify, but yeah.
Yeah, because the kernel does have some challenges. So as you said, like in the past, like the early 2000s and whatever, it was generally as easy as just redirecting the instruction pointer into user space because there was no supervisor mode execution prevention, or
early 2000s,
privileged access never, or anything like that.
Early 2000s was like a stack.
Late 2000s. Yeah.
Yeah, I
guess I'm going a little bit too far back with that one.
Yeah, because at that point, it's like, you could probably still just inject your shell code and jump to it still.
Yeah, I did did come along in like the early 2010, like I think 2011, 2012 is around when SMAP started to gain steam.
Yeah, I'm not sure exactly when it was, so... Oh, that sounds about right. I wasn't paying that much attention to kernel exploitation at that time.
Yeah, but basically, SMAP, or privileged execute never, whatever you want to call it, makes it so that the instruction pointer, when running in kernel context, cannot enter user space, and by extension, supervisor remote access prevention, or PAN, makes it so you can't do an access when you're in kernel into user space. So that made it a bit trickier because after not being able to execute, you would start doing like ROP chain and stack pivoting, where you would just pivot into user space, maybe even, pivot into user space. But SMAP would make that difficult too. So at that point, if you wanted to ROP or get full code execution in the kernel, you would need to have like a KSLR defeat, you would have to have kernel gadgets, and you would also have to pivot the stack into a controlled area that you have, which might be tricky because it's pretty easy to get controlled data into the heap in the Linux kernel, but actually being able to locate that and having an address to it is going to require an even greater primitive, like initial primitive, before you get to the code execution stage. So that's the part that this paper is trying to eliminate with RetSpill. And the idea there is not only can you get user control data into the heap, but you can also get it into the stack, whether that's by having the register, like the user space registers spilled onto the kernel stack, or just having data in some stack frame copied into a kernel stack buffer. And the thing with the stack is, if you can get controlled data into the stack and you have code execution, you can then use a gadget to just pivot the stack within itself. You don't have to pivot the stack into the heap or something. You can just use a gadget that would take you to a relative offset from where you already are. So you can like pop back a bunch of bytes or something to get to a controlled area, or push it forward, whichever. Especially in the kernel, like you have a lot of gadgets that you can use, at least in like x86. So being able to find a gadget that could be useful to you for that would not be very difficult. So that's the basis of their attack. It is a pretty clever idea, I've got to say, and one of the main goals that they had behind this, which is pretty smart too, is they state that a stack pivot into the heap is not super reliable. You have to rely on your data getting there and then staying there, which might not always be easy because a lot of user data that enters kernel space is also ephemeral. So it'll only really stay there for, a certain amount of time, and then it'll get moved around or freed or whatever. But yeah, so it's not super reliable because you also have to get that leak to be stable and whatever. Whereas with the kernel stack, where it's predictable, even if it falls outside of the stack frame, like if it's from a previous run, the stack is predictable. Like that's all there is to it. So the reliability is greatly increased. So yeah, I really like this idea. I did want to bring it up. It is specific to the Linux kernel, but it is a pretty clever idea, and it's worth considering if you're doing like kernel exploitation. I think this is a good trick to keep in mind.
Yeah, at least keep in mind they do call out like somewhat of a downfall of it is not really. Won't even necessarily say it's downfall, but one of the hurdles they do have to overcome is you are like in terms of the amount of data that's going to be copied onto the kernel stack. Because they basically talk about making the syscall, it is intentionally going to be copying that data over, or it might you might be able to create data that's read and then copied onto the stack. They're indirect versus direct options. But oftentimes it isn't going to be a lot of data, so you have a very limited amount of space to pull off like a full ROP chain. They even call out that this usually isn't going to be enough space to actually do your full ROP chain. You're going to need to use this to get yourself into position to do something more from there. It's just going to be kind of the first stage in a sense.
And to be fair, generally you do want to keep your ROP chains as small as possible anyway. Like ROP isn't your end goal generally. You use it as a pivot point to get something better, like being able to map kernel executable pages or something like that.
Yeah, you usually go for more than just the ROP. I think they're talking about usually like this size of ROP chain isn't going to be enough. I'm trying to find where they actually call out some example numbers. Because it wasn't a lot of bytes. I don't remember where in the paper they actually call this out. Yeah, small chains. However, the initial raw payloads enabled by RetSpill are too small for full exploits. This is due to 3 factors and kind of goes into how syscalls are all different, doing whatever, and all of that. So not necessarily a huge amount of data. You'd still kind of need to go a little bit further on your own, but it is a relatively generic technique to kind of go forward with.
Yeah, it softens the requirements for your initial primitive or capability, so it's definitely still useful.
Yeah, they call out here some ROP chains this enables as short as 7 gadgets. So, like, that isn't a lot of space to make all the calls you want.
Yeah.
But yeah, it's interesting because it is an option that simplifies things. I do, like I said, there was a clever idea using kind of the relative aspect of the stack. So you've got the consistency, and then generally speaking, if you're pulling your exploit off around the same time, your stack layout is going to, you're going to be relatively close to your target information, which I think is kind of the main insight they kind of have here with this attack. Is just the fact that the attacker data is loaded in there and you've got that consistency of the stack. So it is nice. In theory, you've also got the aspect of by avoiding the kernel heap, your addresses kind of look correct depending on how you could, in theory, have some mitigations that aren't going to let you return to the heap. So you can't put your rob chain on the heap, try to prevent pivoting. We've seen that in userland. I don't think I've seen that in any kernel yet. Maybe OpenBSD.
Yeah, now that you mention it, actually, I feel like I have heard of that somewhere before.
Yeah, so
I don't remember exactly where, but yeah, like there's no reason legitimately you would ever have your stack pointer go into heap addresses.
Yeah,
so
it feels like something OpenBSD did or something like that. Like that maybe came up during one of those discussions.
Yeah, if there was an operating system to do it, it probably would have been OpenBSD. So probably a good guess.
But yeah, no, I think it's a clever idea. It's not very complicated. It's just a nice insight. That, like, I mean, undoubtedly, they're not the first person to have actually written an exploit this way. I can't think of another exploit that's kind of gone that route, but it feels like the sort of thing that nobody's really documented, but it's maybe been seen before. Or maybe it is totally novel. I guess I shouldn't be trying to downplay their effort or anything. Like, I haven't seen it documented before, is what I'll say. But it does feel fairly simple.
Yeah. All right, so with that said, we can move into our vulnerabilities. So up first, we have a post by SSD disclosure and some issues in QNAP QTS5. So I'll let Z get into this one.
Yep, and this is a JSON parsing issue. So QNAP and there. So they do kind of talk about the age of this vulnerability a bit, being this bug is present across all QNAP NAS devices running QTS and exists as far back as 5.1.0, 2348, and they comment there it's the oldest build publicly available for download, and my initial thought was, oh well, if it's oldest one, it's maybe been around for a while, but that build is going back to March of this year, so I don't know how long this issue has been around for. They are using the JSON-C project, although the vulnerability is not in JSON-C, it's actually in how they're using this library. Specifically, just a little bit of background here. JSON-C's library is going to parse like a given JSON string into a JSON object structure. So pulled that up on screen here, but the important things that you have in here is you have a union, which, as we've talked about many times, is, a good place to look for bugs whenever you're dealing with the union, and the type of data that could be inside the union. So that is the O field of the JSON object, and then you've got the O type field, which is a enumerator, which will contain one of the types that you're supposed to then reference in order to decode the data or the O field. So JSON type is I believe the field is JSON type string, then it should be reading like the C string value. JSON type int should be reading like the C int value. of the union. Makes sense, pretty standard practice to have the type and the union value itself. Nothing too crazy there. But then in one of the actual requests coming in, this QID request v2.cgi binary on the device, it's basically just going to take the first JSON string that they have, and it just loads that into the JSON object. And then it starts trying to read more values coming in, and it just assumes that this first object was definitely a JSON object, because it then, grabs or reads a new string and starts trying to add it into the object with this JSON object add. JSON object add basically assumes I'm receiving a JSON object, not any other type, but specifically JSON object. And I'm going to add this new object into it as like a new field. So kind of looking at this, it's expecting this JSON object to have an O type, so it accesses this LH or linked hash table. It's expecting to be accessing that, and that function doesn't do any actual validation that the JSON object that it's provided is an object. It just goes ahead, assumes that the value in there is a pointer to the object, and it's going to dereference that and try and call like the hash function, hash fn function on it, which basically means if an attacker provides the JSON string that just starts with an integer, when it parses that, it's going to parse into the integer, so it'll set the cint, so you have complete control over what the actual value is here for the O field. And then when it tries to do the JSON object add, it'll treat it as an object, dereferencing what was originally written as an int as the LH table pointer, giving you the type confusion. And from there, we don't get any information about actual exploitability, just the fact they did manage to get the dereference on, hex 4141 repeated. Exploitability, like, feels like you need an info leak to deal with this. You can't just do it on its own. Info leak of JSON parser, one-shot request. Well, no, okay, actually, it's not a one-shot. You can make multiple requests. Although with CGI, I think usually the binary is going to be restarted every time. So ASLR, like, if there even is ASLR, you might have some challenges around getting an info leak, although you might also just be able to get an info leak on a prior request and reuse it here, depending on how the actual server is set up. But definitely a little bit of a challenge to exploit this, just because like you do need an actual memory pointer in order to pass that dereference. But because it is going to be dereferencing a function pointer from there, you absolutely have the potential for the control flow hijack and to actually do something useful with that if you have all the relevant information. But yeah, it's another case of type confusion. This one's relatively straightforward because it's opting to assume that the root object is always just going to be a JSON object, and you're not going to send it, in a sense, malformed data. You'll see their actual data they sent here is just a number followed by a JSON object. So I don't know. I thought it was interesting to see the type confusion in this fairly simple way, but
yeah, I mean, it's fun to see type confusion in C. Like, it's most of the time when you see type confusion issues, it's in C++ where you have, the classes and everything. But like you said, whenever you see unions and you see a field being used as a type identifier like that, it's like, this is where the fun begins. It's a good place to look for sure.
Yeah, it's just unions are hard to get right. Like, you think about it, like, as a developer, it's not that hard. You always check O type and you always just use that, or you even write a wrapper or something to access the data. I don't know, but you think like it's an easy problem. You just always have to use O type before you access the union data. Fair enough, but there are so many edge cases. Like in this case, it's kind of the situation where they just have this utility function that does something that they're expecting to need to do next. And so they do it. And that utility function, of course, they don't want the overhead of doing the type check every time. It's just assumed it's always going to be called in the right situation. And in this case, it's not like... It's a simple problem to solve, but for developers, it's really easy to make these mistakes that kind of skip the checks and just assume they're doing whatever's correct. And it is kind of a fair assumption that your JSON is going to be a JSON object. Like, if you think about every web app, if you've ever done the web app pen testing, like, you generally don't see JSON being sent as anything other than a JSON object. You rarely are going to see, like, I guess I've seen a couple times with line separated JSON, but that's still sending a JSON object, just multiple. So yeah, it's hard to get right, but this isn't a crazy vulnerability and seems exploitable with at least one other bug.
All right, so getting into a bit of a more complex bug, we also have a post from Exodus Intel on a Safari issue. And this is in JavaScriptCore, though it does involve optimization as well as nandboxing. So nanboxing, for those who don't know, it's been a little while since we've talked about it. In JavaScript, variables can be of multiple different types. You can have integers, floats, or references, otherwise known as pointers, internally in the engine. And in order to encode all of this information into a single 32-bit or 64-bit value, assuming the type isn't fixed, you have JS value, which takes an advantage of NaN encoding. So with not a number or nanboxing, the idea is you have the most significant bit is the sign bit, the next 10 are used for the exponent, and the rest are the significand D. And that's used for, I'm not going to go into the specifics of like how the floating point works, but you basically multiply by the exponent in order to get like the final float number. And when all the exponent bits are set, it's marked as not a number. And the reason they do that is that allows you to encode other values such as pointers. So they have a chart here that goes into it. I first saw this chart on the Attacking JavaScript Engines paper by Salo, but it's also in, well, it originally came from the JSC JS value header. So if your top most significant bits are all 0, then the value is treated as a pointer. If it's from 2 to FFFC, it's treated as a floating point, and then FFFE is treated as just a regular integer. And so you can imagine the browser has to be careful whenever it's performing any calculations on nanbox values, because you don't want JavaScript to be able to change a value into, like, basically being able to change the type from like a double to a pointer or something like that, which they give an example of where, say you have some unsanitized large value that starts with FFFE, and then the rest of the bits are all set to 0. When it goes to add the 2 to the 49th constant, that'll overflow to hex 1234, which has the null tag, which gets it interpreted as a raw pointer. Which is kind of what ends up happening here, though through, of course, an optimization issue. So JS Core, they talk about the fact that it has two optimizers, the data flow graph and faster than light, though it's not super relevant here because this issue affects both of them, apparently. And the example they give here is, let's say you have some JavaScript that defines a float64 array with 10 elements, and then it sets the variable to the first element. It can do one of two things. If it thinks that array will always stay as a double, it can just give it a double type and all is fine. But if it believes that it will be used as a JS value, it has to convert it using this box double functionality, which will take the raw double and add this 2 to the 49th power to it in order to do the double encoding. Then it'll subtract the number tag from the double value, which is FFFE, and then all zeros. The thing is here, though, they never check to ensure that that subtraction of the number tag can't underflow. Now, they write here that ideally this wouldn't be possible to underflow, as dangerous input shouldn't really make it this far, because typically it would come from an existing JS value, and because a JS value is already abiding by these rules, it wouldn't be possible to underflow. But if you can get a raw user-controlled value passed in, then this assumption can be violated. You can cause an underflow and end up changing the type of the JS value. And in particular, this compile... sorry, let me try to get it up on screen here. This compile get by val on float typed array function, which is called by the JIT optimizer, does not actually check that the double from the float64 array is a valid sanitized float value. So getting to the POC, which I think it's a little bit easier to walk through the issue going through the proof of concept. They can create an array buffer, instantiate this big UN64 array buffer with that previous array buffer backing it, as well as a float64 array with the same array buffer backing it. Then they define a trigger function, which basically just runs a for loop and will pull the value or reference from an array and return it. They can call that a bunch of times with a regular float value, train the JIT compiler into basically getting it hot pathed, and then they can use the big UN64 array to write this malicious double value in there, so like the FFFE and then all zeros value, trigger it again, and what'll happen is that malicious double value will get used, it'll cause an overflow, and the lowest 32 bits of the double value are treated as a pointer to a JS object, which when that trigger function returns that reference, basically gives you a free fake object primitive. You can get any address treated as an object. Now, it's still a little bit tricky to abuse at this point because ASLR is in play, and you do have to craft a pointer directly. And you would think that, if you craft an invalid pointer and try to use it, you'd be guaranteed to crash. But they found a pretty neat trick, and that's the fact that you can basically write a compare function and get that JITted. And if you like just get it to compare this pointer against a reference to another object, you can basically use that as an oracle to determine if your address is a valid address. So yeah, you just write a very simple compare function that takes arg1 and arg2, compare arg1.x to arg2.x, and use that to check your faked object against valid object to brute force the ASLR, which in user space, where your pointers will be like in the 32-bit space, that's not too unreasonable. So yeah, I thought that trick was pretty neat. Ultimately, this does like it. What's also cool about it is the fact that this bug is technically a fault in JSCore, where they don't do any verification on the value coming in to make sure that it's a proper float value. But it's being taken advantage of by leveraging the JIT compiler to get that like raw value through. So it's leveraging some different parts of the engine to get the exploit to work.
Just kind of one, I think, clarification, but you mentioned in user space the pointers will be 32 bits. I believe you mean just like inside of the JavaScript.
Sorry, inside of the browser.
Yeah, inside there it'll be 32. Just being user line doesn't mean it's 32, but the whole pointer compression and stuff. Yeah.
All right.
XCD80S is pack enabled. I don't think they're really talking about it as an exploit in the context of iOS, although I mean it is Safari, but I don't think they talked about well, I guess we observed that on iOS, so they didn't really talk about pack here at all, so I'm just assuming they either don't talk about that because they have their own techniques for it, or didn't actually exploit in that way at all, like on iOS.
Yeah, one thing I was just trying to quickly check is I wasn't sure if pack worked inside of the browser renderer, because I could see pack being a huge like pain to support in the context of the browser where you have so much going on. But I can't seem to find a solid answer on that, so I'm not sure.
Either way, they don't discuss it.
If you were trying to get pack to work, you would want it to work on WebKit, but yeah, that's not an area I'm super familiar with, so I can't really comment on it. But yeah, as he said, they don't mention pack here, so yeah. But yeah, it's somewhat of a complex issue, but it's just because they're taking advantage of multiple aspects on the browser, and the way their exploit worked is pretty cool. I do want to mention there is also a talk that was given on this in October, which they link off to at the top of the page. There is some information in the slides that isn't really in the blog post that I think should have been included. Like, it makes it a little bit clearer to understand. For example, their ASLR bypass, I found the information about doing the compare. I was able to get a more solid understanding of it from the presentation rather than the post. So yeah, I did want to shout out that that's there as well. All right, so getting into our last issue, we have a post by Thallium on achieving an RCE in Steam, and I'm going to let Z get into this one.
Yeah, and let me apologize if that audio just came through to you guys from the video. I think I usually have it muted, but I have a new audio setup, and it might not have. So if you heard that little blurb of audio, I apologize. That was from the talk for that, which I was trying to close off. But yeah, let's jump into this. It's a remote play or remote code execution in Steam through the remote play protocol. I'm not going to go through a lot of the background here, but it does include some background to remote play and the implementation, and also building kind of their fuzzer for it. They went and built their own fuzzer, kind of did their own implementation of some aspects of the protocol so their fuzzer could just generate these messages, send them to... actually, let me just bring up their fuzzer architecture, which is somewhere in here, but I must have scrolled by already. Okay, for some reason I'm not seeing the image I want to see. Nonetheless, network protocol. You've got the client, you've got the server side, or a host side of it is the server side, and then you've got client. People can kind of use that. So one player might host the remote play session, somebody else and they're going to have like the video stream being sent, and then somebody else, the guest player, is going to actually have all like the keyboard, mouse, controller inputs actually play, like do the remote playing.
Yeah, I mean, it's cool for some of the older games, especially with like split screen or like that kind of mechanic. I've actually used it once before for a game that had that, so that's primarily where you would use it.
Well, so I think this also just lets you, so like, okay, so I haven't used it, but I also assume like you could just be playing like your own remote device and just kind of having access to your own stuff that way too. But yeah, also for as you said, like local multiplayer remotely. Anyway, we'll jump into the actual vulnerabilities here. Unfortunately, when I read this one, I saw they had like the heap overflow and stuff. Turns out the remote code execution, though, is actually a fairly simple issue, and it's not a binary issue. And speaking about the fuzzer architecture, actually, I've got that up here now. They had their PB fuzz, which is has like the protobuf stuff and protobuf mutator, sends things to the fuzzer, which sends the packets to their custom implementation and then actually sends it off to their target. And they have some other aspects in there, but they go through their whole fuzzing implementation, which is worth a read if you're interested in that. It's not a very complex fuzzer. But they did kind of a lot of the work themselves. They weren't like, I don't think they really reused like libfuzzer at all. Just had to double check on that since I was saying about the protobuf mutator. But worth a bit of a read for the background. Getting into the vulnerabilities, as I said, this first one is a path traversal file write in C set touch icon data message. In this case, the idea with this message is if you want to share images of like the icons for whatever, it's just going to send this set touch icon data, which lets you provide, well, data icon. And what kind of matters here is that it's going to get the icon name value out of the data. And if that name starts with a @ or what matters here actually is if it doesn't start with an @ sorry, it will treat whatever string you provided as the icon name as a relative path on the file system. So standard path traversal, .. out, and you can go ahead and write your data to any file you want that it's able to write. They got their remote code execution by just overwriting, like going into program files, Steam, and Win HTTP DLL to overwrite that DLL and get code execution on the client. So fair enough, straightforward, not really a binary issue. Getting into some of the binary issues, I did come across some format string bugs. In this one, they have some of these the value name underscore location variables, this mini profile and this avatar location. Both of those location values are used as the format specifier in a printf. I think the idea here is that would provide like a URL with a single parameter inside of it, like a single %d or %s or something, and then it would take that URL, inject the appropriate like player ID or whatever into it, and then it makes a curl request to that finalized location and expects some data back. I think in both of these cases, it's expecting a JSON payload back. But effectively, you're getting a curl request with controlled data plus format string bugs. So you're able to leak. So if you include just like a %x, or I think their example is %08x, but effectively doing x just padded out on 8 bytes. So kind of pointer being leaked out there. Example here with the mini profile location, set that field to this string leak, and then those bytes. What happens is when curl fails, it'll send a debug string, and that goes back to the host. So the host is able to see this debug string of whatever data gets leaked off the stack. So you could leak plenty of data out of that, as long as it's something that curl's going to get back in its error message, basically. So maybe want to make it look like a domain or something. Either way, you're able to leak kind of that relative data. And it's a very similar issue with the avatar location. And then on both of these, if you get it to an actual website, it's going to expect the response to be JSON. And it's going to try and parse that JSON. If the JSON parsing fails, it's basically just going to give you an error that is could not parse, in this example here, could not parse profile data, syntax error near, and then the entirety of the response content gets dumped out with that too. Ideally, so somebody debugging it could see, hey, here's the data it was trying to parse, and you can kind of figure out why it failed. But that also means any request that you make, because you control the URL that's going to make this request to, any request it makes, any GET request, you can get the response data to it. And they say that gives a so-called SSRF primitive. They would consider it kind of a client-side or CSRF. Although that's client-side and not cross-site, but they would call it that because it's on the client of this. Regardless of how you want to define the request forgery, it is a request forgery. I feel like in this scenario, it doesn't seem as useful as other request forgeries. So it is using curl, so it's not like you're going to have it on the client side of a browser where they're then making requests potentially with their cookies. So you're not getting that. You're not getting access to anything logged in. You may be able to access internal services, but you're probably not having this used like in a corporate environment where they're doing their remote play in there to get access to like internal services. But it might be like it definitely could happen, and there could be things to leak on there. But because it's a home network, or most likely scenario is going to be like the home network, most like gamers aren't running a lot of really sensitive services like that. There's probably some things they could go for. But it does feel like a mitigating factor here. Like, it's still an issue. It is still a request forgery and could still be exploited. Just the realistic aspect of it does feel a little bit off to me, but definitely still an issue, and there are cases where it could be exploited. Rudimal mentions a bit surprised that was writable, speaking about the DLL that was overwritten. Yeah, I'm not sure if this was written or if this is running as admin, but also because they are kind of the Steam program, I'm assuming that's possibly why they targeted the Steam's owned DLL in that folder specifically.
Yeah, because like Steam has to be able to have the capability to write there for like doing updates and stuff, right? So,
although that's usually going to prompt you for
segregate
admin. But this very well could be running as admin given the other level of access they need to like all the devices and all of that.
Yeah.
I don't know if the service is. And when I was reading through this, I actually had kind of a similar thought, like, oh, I'm surprised they're able to write into program files, but I don't think they really talk about specifically why that is the case. Just they notice that it tries to load this file and it's not found, therefore, oh yeah, the file didn't exist. I kind of overlooked that, so they're writing new files. So it's still interesting to write into program files because that does require admin, but I'm guessing either because it is the Steam program, writing into the Steam program files, getting in there, or it's running as admin already. I guess if it was running as admin, they could have targeted System 32 though, so either way, they were able to write to that, but yeah, I kind of had some questions about that too. Specifically about how that aspect worked. But since it's not here, can't really say for sure. Anyway, so we have the request forgery issue. Yeah, fair enough issue. It's kind of fun to see, especially kind of this scenario for the request forgery to be happening. Like, there is kind of that client side, server side, like it is limited, more like the server side request forgery, but it is technically a client that's making the request. So yeah, I mean, there are ways to pivot it. And I guess like on an internal network, you are going to have more access to potential IoT things, which generally tend to be pretty insecure. If you have multiple requests through, you can exfil information about the local network potentially. There are definitely ways to abuse it, but I guess that's not even a binary issue, so maybe not worth as much discussion as I've given it. Getting into another binary issue here, out of bounds access in this CE remote play together group update message. And that is actually the same message that we were just talking about with the locations for the request forgery. And I think that was the same as these. Yeah, it's the same one as used by the regex, the format strings. Anyway, let me find where we are here. So in this one, the scenario is a little bit different. What happens is you have, when you send this message, a group update message, it has this player index, and the idea of player index is that is the index into the I'm showing you this as a protobuf, but basically this can be any number of, or I guess this one technically is a repeated player's object. So they have the player message that's just going to be repeated in this. So they have an array of players and a player index. Player index points to who is the host of, all the players connected. Which player index is the host player? So it can just reference directly in that. And then when you send that update, it doesn't really do anything there, but when you send the set streaming client config message, that will actually trigger the bug that ends up iterating over the players and ultimately can end up accessing the player at the player index. It does this specifically as it iterates over all of the players, has this do while loop, iterates over all of the players. And then if it gets on the last player and still hasn't reached like player index is still higher than the current index or the current K value. It just goes and fetches the player directly, accessing that. So you do have, and then it calls this update player state with that player object. Once it has the host kind of found there, or iterated in this case. Either way, it reads that. Unfortunately, they didn't really have much of an exploit out of this. Despite it reading out of bounds, it doesn't do anything interesting with that out of bounds read. It'll access that object, but it doesn't do any further writes based off of it or anything like that. So, kind of had a bit of a limited impact off of it. Unfortunately, the player stats method doesn't do anything really interesting with the player structure. Then they use it more as a way of highlighting some of the more stateful bugs, since it requires two messages, or at least those two messages, to come through as part of their fuzzing. But it is kind of it could be a nice situation because it is reading kind of the fake data or out of bounds data. They kind of talk about using that potentially as a type confusion if they had like an ASLR leak and could structure things properly there, but it is what it is in this case. Second to last bug, keep overflow in YV12 video frames. Again, another thing that you do with this is it's going to send video data. I mean, that's part of like the intended functionality of remote play is to send the video over. So host can decide what codec it's going to use, and one of those codecs is just to send raw video or it's just sending the pixel data. That pixel data can be formatted in multiple ways, but in the YVU setup where it's sending, the nice example here of it's kind of, you send the brightness information, then you just send a blue and red projection on it that get converted rather than it being like a RGB. Either way, in sending that, what ends up happening is a fairly classic issue of just not checking your bounds. So it's going to take the user data that gets sent, and this video format packet or message contains, what format it's going to send in, and then just width and height. That's all attacker controlled. So what ends up happening is when they end up sending the data later, it's going to get the offset to the Y plane, the U plane, V plane. It's going to get the offset to each of those, and it's going to calculate that based off the width and height provided without doing any bound check to, did they actually send this much data into it? Meaning that when it goes to render these frames, it'll potentially end up reading out of bounds. And just rendering these frames as either garbage or corrupting part of it in some examples. This one is, or feels a bit problematic to actually exploit. It's a fun issue to see. I really like these things where you get data leaked out in images. You know, we've seen that on the web a number of times, and I really like those info leaks. This one, unfortunately, because this is on the client side, it's producing these bad images, but the ultimately, like, the attacker who's sending this, it doesn't get to see it. It doesn't get sent back to them with, like, the data filled in or something like that. So does this wrong, but they don't get to see it. They talk about maybe being able to social engineer someone. You do that, and then you ask the client to press F8 to get, like, this performance overlay, and that apparently soundly uploads a screenshot of the window so they could leak information that way. Which, I mean, a single key press, if somebody complains about it, I could understand, like, somebody maybe falling for that, but it does take social engineering to get it. So I like the bug. I like that style of issue where it's leaked in this way, but it doesn't feel as practical to me. But still believable.
Yeah, it's unfortunate that the binary issues weren't as practical, but especially when you have these sorts of setups where you have the client server and you're trying to attack across a connection like that, like it's just a lot harder to pull memory corruption off and be able to exfiltrate data like that.
Yeah, I mean, any sort of remote exploit where, like in this case, just can be tough. I guess not any remote exploit, that's kind of a different thing. But yeah, the scenario is interesting for looking for these bugs. The last heap overflow that they had is a pretty small heap overflow, but heap overflow in C remote hidden message. So human interface device. The host will ask for the hid input reports, such as saying what buttons are they pushing and stuff. Again, kind of a necessary feature. And they'll send a message over saying device start input reports, and that just, what device. The device already has to be open at this point. They talk about another message needing to be sent for that, but give it the device, then you give it a UN32 corresponding to the length of what size the data should be that it sends back. The problem here is, while that length cannot be more than 27 bytes, in the serializing logic where the gamepad is going to, or where it's going to write out the actual inputs from the gamepad, it apparently doesn't check if length is big enough for what it's writing. So while it does make sure the buffer isn't too big, I guess, which feels like the wrong place to do a length check, the actual pack that writes into that buffer doesn't check if the buffer is big enough to actually store it. And so with that, it can overwrite just within, like, that 27. So if you gave it, I suppose, like a 1 byte buffer, it could overflow like 26. So it's not a huge overflow. And the other challenge on this one is that it's the client that controls what's written there. It's the data from the gamepad. So exploitability feels very, very difficult on that one because the write is controlled, or because it's only a linear overflow and the data is controlled by the victim. Feels like that would be very hard and probably impossible to exploit. But just another bug that they found in looking for this. They do also talk a bit about their whole chain here in terms of their disclosure timeline. Most noteworthy part of the disclosure timeline to me was just the fact that Valve was taking quite a while, and they want to disclose this with like they gave a talk somewhere, I think it was.
Valve taking a while? I have never heard of that before.
In fairness, they called that out. They said, like, I had not heard good things about Valve and had read many complaints from other security researchers about them being slow. And they also call out, what I thought was interesting, they call out that Valve it encourages the finders to disclose their reports if the team is unresponsive for 6 months, which I didn't know that was kind of a thing Valve encouraged, but kind of a noteworthy program, I guess, to encourage their own teams to actually deal with these issues, because it was shortly after he did the presentation. See, it's the bug's been ignored for like 6 months or whatever. I didn't go and check the actual timeline, but presumably more than the 6-month period, it's been ignored, and then just a few days later, 5 days later, they triage the bug. So, I mean, I think it's nice. Rudimal mentions, I think H1 encouraged it. So what they mentioned here was that the H1 analyst informed them that Valve didn't reach the final decision regarding the report, and then warns them that disclosure would go against H1's policy. And then they indicate that Valve's saying is that they encourage the finders to disclose it. So that doesn't sound
it says like... there, which is a bit ambiguous. Is there referring to Valve or HackerOne? I didn't click through that link. You see their guidelines do state, is that Valve's guidelines or HackerOne's guidelines?
That's fair, actually. I kind of read this as Valve, but yeah, that actually goes to HackerOne.
Okay.
Which is fair to call out. So, I mean, this is their philosophy, so I don't see exactly where it mentions, like, the 6 months or whatever. Or if it even calls it out here. Actually, I don't see it in there, but this does seem more like their guidelines, so a specific policy from Valve may be different, even if it's probably under here.
Yeah, I'm just trying to look through as well.
Okay, so yeah, it's this last resort. If 180 days have elapsed with the security team being unable or unwilling to provide a vulnerability disclosure timeline, the contents of the report may be publicly disclosed by the finder. We believe transparency is in the public's best interest in these extreme cases. So that does sound like that's coming from HackerOne and not Valve, so my bad. As I was reading that, I read that there as being like as being Valve's policy. I didn't actually click through on it, which is interesting, but this does read to me more like guidelines and not necessarily the policy that every program is going to follow, but what HackerOne would like their policies to be and what they encourage their policies to be. Because we have absolutely seen reports through HackerOne and people disclosing things early and all of that. I don't know specifically on the timeline there because it's not really the information I was paying attention to, but I've never seen this really mentioned before, so it feels like most programs probably don't follow that guideline, even if it is kind of what HackerOne would like. So I'm not sure if this is really the binding policy. That's it. I'd have to kind of read through this here. Because I feel like the specific program should kind of take priority in terms of what they decide the guideline should be on disclosure rather than just the HackerOne thing here.
Yeah, this is where like my lack of like experience on HackerOne or whatever doesn't allow me to comment too much here. I'm just kind of going by what we're reading because I've never submitted through HackerOne or like ran a program on it. So
yeah, and I haven't been involved with running a program or submitting either. So I'm not too sure. I'm just reading this now, so I don't know. It reads to me like this isn't necessarily the enforcement, but at the same time, they do comment here by submitting a vulnerability to a program. You acknowledge that you've read and agreed to these guidelines, so that does make it sound like it's enforced, but given everything else I've read on HackerOne, it also feels a little bit off. This whole discussion would probably be better on our bug bounty episode, though, but either way, unfortunately, I misread that and thought it was talking about...
no worries, like I said, it was just a little, it's just a little ambiguously worded.
Yeah, I didn't even notice that. I just immediately filled in Valve since we're kind of talking about Valve through all of this. I assume Valve actually had that really nice policy, but if it's HackerOne, it's a bit more expected that they have a decent policy like that.
Yeah. But yeah, I mean, like you said, Valve's had that reputation, and I think they are improving on that, but it's still pretty rough.
I've heard mixed things about their improvements, to be honest.
Fair enough. I remember we did see one or two reports that were suggesting that they were getting faster with getting around to at least communicating back with researchers. Maybe not fixing issues necessarily, but at least not leaving them, hanging for months on end. But yeah.
Yeah, I mean, the thing about Valve is it is one of the few bug bounty programs that have binary targets and pay out, or potentially pay out something decent. So yeah, in this case, like, we're spending a lot of time talking about the bounty program here, and that's because Valve does kind of have a somewhat interesting bounty, or potentially interesting bounty for those few here.
For sure. Yeah, I mean, a fair amount of issues, fair amount of binary issues too, but just unfortunate scenarios they ended up being in for actually exploiting them.
Yeah. The exploitable
though the social engineer aspects aren't completely out there, they are somewhat reasonable. Some of them, like the F8 one, but yeah,
I'd agree. Like, they could be exploited. Like, any one of these could, well, not any of them. Obviously, some of them aren't going to be exploited, like, aren't exploitable. But those that are exploitable, like, the social engineering could be done. It's just something that kind of downplays it in my mind.
Yeah. All right, but yeah, that's all the topics that we have for today. So as always, thanks goes out to everyone who listened. If you want to go back and check out past episodes, you can find them on YouTube, Spotify, Apple Podcasts, and more links on Anchor. Feel free to join our Discord and follow us on Twitter. Links to those are down below or in the chat as well. Once again, this is our last episode of 2023, so happy holidays to everyone out there. And we'll see you again in the new year, and that's when we return on January 8th and 9th.